Okay, we're ready for 1.4, geometry, and this section is on polygons. A polygon is a closed figure in a plane formed by connecting line segments. And you classify a polygon by the number of sides it has. Most of these you already know. On out here, some of these might be kind of obscure that you've never heard of. So, penta is 5, hex is 6, heptagon is 7, octagon has 8 sides, nonagon has 9, a decagon has 10, an undagon has 11. You might never have heard of that one. A dodecagon is 12, and in anything greater than n, or greater than 12, we call it an n-gon. N in this case always stands for how many sides it has. So a 25-sided figure is called a 25-gon. To name a polygon, you list the vertices in consecutive order, either clockwise or counterclockwise, it doesn't matter, it just needs to be in order. So let's look at this polygon. This is a pentagon because it has 5 sides. And I can name this A, B, C, D, E. I could name it D, C, B, A, E. As long as the letters are consecutive, meaning one right after the other. Okay, so these two right here, because they're one side right after the other, those are called consecutive sides. These two angles, because it's one angle right next to the next one, are consecutive angles. This and this, because they're vertices one right after the other, those are called consecutive vertices. So a polygon can be convex, meaning all the diagonals are on the inside, or a polygon can also be concave. And the way you're going to remember concave is that it sort of caves in. Like this is the polygon right here. This is the polygon, and it sort of caves in right there. This is the polygon. And notice that on these, you have one or more diagonals that are on the outside, because the diagonal connects one vertex to another one. All right? Two polygons are congruent if and only if they are the same size and shape. If polygons are congruent, then their corresponding sides and angles are congruent. And also, we can say that the converse of that statement is true too. If corresponding sides and angles are congruent, then polygons are congruent. I just used a term you might not know. Converse statements. So we're going to be looking a lot at if-then statements in geometry. So if, this is called the premise. Then, this is called the conclusion. If-then statements. The converse of this statement is you just trade places with the if-then parts. So the new statement, the converse of this thing, would be if the corresponding sides and angles are congruent, then the polygons are congruent. Keep in mind, and we'll talk about this more later in a later chapter, that the converse of a statement is not always true. In this case, the converse of this original statement is true. Okay, so let's say we have these two quadrilaterals. This quadrilateral will be named CAMP. This one is called SITE. Get this? Clever, huh? Campsite. So the way, remember when I said the way you place these letters is very important. In this case, I know that angle C is congruent to angle F. Angle A is congruent to angle I. Angle M is congruent to angle T, and P is congruent to E. P and E have the same marking. M and T have the same marking. So I know that those are corresponding congruent angles. Same with the sides. CA is congruent to SI. AM is congruent to IT. MP is congruent to TE. And PC is congruent to ES. Very important that you put these letters in the proper order. Just a side note for problems on this section, remember that the perimeter is the sum of the lengths and sides of a polygon. Alright, here's some more terms that we need to talk about. Equilateral polygons are polygons whose sides are all the same. Equilateral means side. Equa obviously means equal. Those are three examples of equilateral polygons. Equiangular polygons are polygons whose angles have all equal measure. All these angles are the same. All these angles are the same. So if you have a polygon that's both equiangular and equilateral, we call those regular polygons. So all the sides are the same, and all the angles are the same. Sides are the same, angles are the same. So this is a regular pentagon. This is a regular triangle. We call that an equilateral triangle. And a regular quadrilateral is a square. Okay, we're gonna work through that table on worksheet 1.4. The first, I know it's like 1 through 10 on 1.4, and we want to look at the number of diagonals in a polygon, and I'm going to show you how we develop the formula to find how many diagonals are in any sided figure. So let's do the ones that we know for sure, and we can draw them without any trouble. So we know that a triangle has 3 sides, but it doesn't have any diagonals, because remember, a diagonal connects any 2 vertices, any 2 non-consecutive vertices. So there are 0 diagonals there. A square has 2 diagonals. A pentagon, there's 1, 2, 3, 4, 5. I could draw the hexagon, but you're just going to have to take my word for it that a hexagon has 9 diagonals. Anything greater than a 6-sided figure, it's really kind of a pain to draw the diagonals in, because it gets your picture just gets really messy. So we're going to develop a formula for finding the number of diagonals. It's going to make our life a little easier. I'm going to go through this fairly quickly. Don't freak out if you don't understand it. We're going to spend a lot of time on nth terms for, I think it's chapter 2 when we start doing it. Alright, so here's my method. I want to look at the differences between my outputs. The difference here, I added 2. I added 3. I added 4. This is what we call the level 1 differences. We're looking for these to all be the same. If it's not the same, then you go another level. So I'm going to go another level. I add 2 plus 1 is 3. 3 plus 1 is 4. These are the same. So because those are the same, I know that I have level 2 differences. What does that mean? It means that our formula has an n squared in it. If it had been a level 1 differences, then we'd know that that would be a linear function that represents that formula. Okay, so now we want to look for a pattern. I'm going to go ahead and repeat inputs, outputs. 3-sided figure has 0, a 4-sided figure has 2, a 5-sided figure has 5 diagonals, and a hexagon has 9. All right, what we're looking for is a connection, a pattern between the number of sides, which is n, and the number of diagonals, and we call this the nth term. Because I have level 2 differences, I'm going to go ahead and multiply this row by 2, because right now I can tell you I don't see a pattern. And I'm going to rewrite the table with these numbers multiplied by 2. So now my 2 becomes a 4, my 5 becomes a 10, and my 9 becomes an 18. And if you look down here, I don't think you can see it. Okay, 0 is 3 times 0. 4 is 4 times 1. 10 is 5 times 2. 18 is 6 times 3. Notice the pattern. This is 1, or 0, 1, 2, 3. That's a pattern going up by 1. These also go up by 1, but more importantly, these numbers represent my n values. So I'm going to rewrite this using all n's. So 3 is n. If n is 3, then 0 would be n minus 3, because 3 minus 3 is 0. If this is n, then 1 is n minus 3, which is 4 minus 3 is 1. If n is 5, this number is n minus 3. 5 minus 2, or 5 minus 3 is 2. Now I have my pattern, because these are all the same. So you might say, oh, well, the formula then is n times n minus 3. But don't forget that I had to multiply by 2 to get these numbers, and I have to undo that now in my formula. And how I undo that, multiplying by 2, is dividing by 2. That's what that's saying. So there's your formula for the number of diagonals in and n-gon. Sorry. You're going to want that formula in your notes. That's a hint, because it's going to be on the test. So, if I have a heptagon, 7 sides, n is 7, I'm going to use my formula. It's going to have 7 times 7 minus 3 divided by 2 diagonals. Well, 7 minus 3 is 28, or 7 minus 3 is 4. 4 times 7 is 28. 28 divided by 2 is 14. A 7-sided figure has 14 diagonals. Pretty cool, huh? And that is it for 1.4.